Okay, yeah. So welcome to this distinguished lectureship entitled Global Warming or Global Cooling in the Last 10,000 Years, the Holocene Temperature Conundrum. So I'm Shuang Zhang, the Associate Dean of Science in China and Global. So most of previous temperature reconstruction of global annual temperature shows an early Holocene warming followed by a cooling trend through the middle to late Holocene. This global cooling is puzzling because it is opposite to the expected and simulated global warming trend due to the retreating ice sheets and the rising atmospheric greenhouse gases, leading to the Holocene temperature conundrum. Critical examination of this apparent contradiction between the reconstructed cooling and the simulated warming points to potentially significant biases in both the seasonality of the proxy reconstruction and the climate sensitivity of current climate models. So in this lecture, Professor Zhenyu Liu will discuss a new analysis of tropical-subtropical mean annual SST reconstruction, which produces a cooling trend after using a method to filter the seasonal bias signal in the original SST reconstruction, and the conundrum is likely resolved over the ocean. So Professor Zhenyu Liu is a Max Thomas Professor of Climate Dynamics and the Professor of Bird Polar and Climate Research Center in the Ohio State University. He's a fellow of the American Association for the Advancement of Science, American Meteorological Society, and the American Geophysical Union. He also received the Willis Associate Award, UW Medicine, in 2000 to 2003. So Professor Liu's research focuses on climate dynamics, ocean atmosphere-land interactions, dynamics of oceanic circulation, paleoclimate modeling, Earth system modeling. He has published nearly 400 publications and 77 AGU journals on past climate dynamics, climate variability, and ocean atmosphere interaction, and climate ecosystem interactions. So without further ado, I will now pass the floor to Professor Liu. So let's welcome Professor Liu.
Thank you very much, Professor Zhang, for the introduction. And I thank the university for inviting me, giving this lecture.
Oh, sorry. Oh.
Oh, okay.
Yeah, sorry.
Yeah, okay, okay. Yeah, thank you, Professor Zhang, for the invitation, and the university for the invitation for the lecture. And I also thank everybody spending your precious Friday evening time with me. Hopefully there's something interesting you like. So yeah, I'm going to talk about the topic that actually started about almost 10 years ago, more than 10 years ago. And I think on and off, and finally leading probably a more conclusive conclusion. And the informal title is Global Warming or Global Cooling in the last 10,000 years. That was actually my original paper title for PNAS, but the editor at the final stage said, you cannot have a question mark. So have to think about something else. So then I said, okay, then I said, okay, maybe it's a Holocene temperature conundrum. So the paper title is temperature conundrum. So just briefly, the Holocene is last 10,000 years of our history, okay? Okay, yeah. Just to get started, this is a global annual temperature observed with all the instruments we have for the last about 100 years since pre-industrial, okay? And this is well known. There is a global warming of about 1 degree happening the last 150 years since pre-industrial. That's, nobody argue about that. The hard part is that, is this caused by human activity or this is just natural variability? Because that's a harder question. So to me, one of the most convincing evidence showing this is caused by human is coming from this paper. For some of you working on climate might know this as a nickname, hockey stick. So this is a construction because before pre-industrial, we basically don't have observation of temperature, instrument of temperature. So therefore, you have to rely on the paleo proxy, tree ring, ice core, all different kind of sedimentation, all different kind of proxies. This last 1,000 years, mostly based on tree ring. And you can see that the temperature was actually a little bit cooling. Now that's what people refer to little ice age. Then after pre-industrial, it coming back. Okay, so so the pre-industrial warming, this part is really abnormal in the context of global temperature change of last 1,000 years. And this is, even beyond the natural variability here. Okay, so there are decades, even centennial warming, cooling, little ice age, but pre-industrial warming is very abnormal, very rapid and very big amplitude of that. So I think this is one of the most convincing evidence suggesting, observational evidence, suggesting that the pre-industrial warming from like this is caused by human. Okay, now we can extend this further back. This is 1,000 years for 10,000 years. That's a Holocene. Okay, now in this context, the conundrum to produce is this. This I'll show you later. This is a construction at 2013 of global temperature in the last 10,000 years. As it presents, you can see that the global warming, global was very warm in the 8,000 years ago. And even comparable to present day, not pre-industrial, comparing to present day after already 300 ppm CO2 warming. Okay, so if this is true, it implies before human activity, we can have, and you will see later in this part, there's not too much other forcing. The natural variability can go to very warm compared to pre-industrial and present day. So that's that will be has very important climate implication. Okay, but now let's go back. Just for some of you might be interested. This period actually is quite interesting because the most major civilization started about this time. Okay, from Near East, Egypt, and India, and China, all the major civilizations starting about this time. Okay, 5,000 to 6,000 years ago. So it's interesting in that context. Now we go to a little bit just about the physical mechanism. This is the picture I showed you before in the 10,000 years Holocene. Okay, we may have warming then cooling. That's what I suggest by this reconstruction. But you're looking at back on an even longer time scale, 10,000 years, 20,000 years, 30,000 years. Now this is from Greenland ice core. From Greenland ice core isotope, you're calibrating the temperature, and the Holocene actually is very quiet compared with previous periods. Previous periods, you can have climate change abruptly for 15, 20 degrees, okay, on Greenland, okay? But in the Holocene is very quiet, okay? Now, part of the reason, if we go back, this is more on the mechanism part. And just to show you a little bit, since about 20,000 years ago, that's called the last glacial maximum. That's when the low-entire ice sheet in Wisconsin, extending all the way from Hudson Bay to Wisconsin, and building about a 4-kilometer ice sheet, okay? And the sea level lowered, equivalently, sea level lowered by about 120 meters. So it's a huge change at that time. And at that time, so you can see Greenland from last glacial maximum warmed towards the Holocene, okay? In this period, we know there are major forcing. One is atmosphere CO2 increased by about 100 ppm. And probably associated with that, there's aerosol. You can detect that the aerosol was more because drier, so it's more aerosol, so that's reflecting sun. So it's also cooling effect. And there are also ice sheet there reflecting sunshine, so you get less insulation. So it makes it colder, okay? So we are not surprised to see this is warming up. But major ice sheet, all of them, basically remain unchanged in the Holocene, okay? And there in the Holocene, there's no major big forcing. The really one big is this solar insolation. This is a summer insolation in the North Hemisphere, let's say 65 degrees. This is a winter insolation. You can reach about 8 watts per square meter. That's about 5% of our current insolation we have, okay? So this insolation, but an important thing to notice that this insolation is seasonal. This is because this insolation is caused by the so-called precessional cycle of the Earth. That is, currently, we are closest to the sun in January 7th. And therefore, in June, actually now, we are further away from the sun. So, but to the North Hemisphere, we are summer. We are further away from the sun. So we actually get less insolation in the summer than 10,000 years ago when it's the opposite. This is 20,000 year cycle, okay? So 10,000 years ago, June is a time of perihelion. We are closer to the sun. So imagine we are in the North Hemisphere. We are closer to the sun. We got a 5% more solar radiation. In winter, we are further away from the sun. So we got a 5% less solar radiation. So in the North Hemisphere, the entire seasonal cycle is increased by about 5%, just the forcing, right? That's the dominant forcing generally. But annual mean, there's no net change because you're just, you all year around average, no change. And that's a very important point because this is a seasonal, very strong seasonal forcing. This temperature is supposed to be, when they construct it, they think it's annual mean temperature, okay? So then you have this problem. In this period, you don't have major forcing. Actually, CO2 increased a little bit. Ice sheet reduced. Reduced ice sheet, it helps warming. CO2 increase a little bit, helps warming. Solar radiation, there's no net forcing to the global annual mean. How can you produce this cooling, right, against the increased warming and the ice sheet forcing effect? Now, this actually is all hindsight. And this kind of construction, Holocene thermal optimum, has been a classical picture in like paleoclimatologists when they have the data. Many of them produce this, okay? It's a classical picture. But now you sit back, think about this physical question, it's actually a puzzle, right? How can it be possible? The forcing is warming, CO2 increase a little bit, ice sheet retreating, both helping warming. Orbital, there's no net effect, but then how it could produce cooling, right? It's actually not obvious. Now, of course, I didn't realize this at first, like many people just think this observation. For me, it was actually about 10 years ago, I was reviewing a paper by Dr. Jiang Dabang from Chinese Chemical Science. He says title is that considerable model data mismatch in temperature over China during the mid-Holocene. That's 6,000 years ago. What he showed was that all the models show 6,000 years ago, China is cooling. Okay, should be somewhere here, cooling 6,000 years ago. But the observation, the proxy observation shows it's warming. So he said, there's considerable just model data mismatch. Well, he didn't say data wrong or model wrong. Probably he said model wrong. That was first impression. I reviewed the paper. I thought it's quite interesting, and but that gave me a puzzle in my mind. Why is it? Are all the models wrong? Remember, all these models are state-of-art climate model have been used to predict future climate. We are using, okay? So if all of them are wrong, then we better be careful about this model, okay? Now, the other thing made me think about this. Then right after that, it was the IPCC. I think that's that's AR5. I can't remember AR5 or AR. they are, Axel Timmerman is one of the members writing the summary. And at that time, since I did a climate simulation of the last 21,000 years, and he heard there was a reconstruction of global climate change, temperature change of this. And he put our model with two other models together with observation. He said, well, this looks really interesting. We should put this as one of the figure in the introduction chapter of the IPCC AR. I can't remember AR5, AR1, that one. So we put this figure together, and he said, wow, looks great, let's do that. But now, because I remember that paper, review paper, I look at the Holocene, you see an interesting feature here. The observation shows the cooling. As I said, the observation shows cooling. But all the three models actually shows warming, right? So yes, during the deglaciation, they are more or less the same. But in the Holocene, they are completely opposite, okay? Then I said, well, we will be careful about this. Then we conclude that we don't understand this, forget it. So this figure is not in that IPCC report. So here, then actually this paper, Marco, the paper actually published a little bit after we discussed that IPCC report. They know the data informally, and but then it published. So this is most of the data based on the coastal data, because you want to have the good resolution, and which is hard over land. So they have the coastal data and sediment data constructing temperature and showing this. So mostly based on marine proxy. So then it comes to me with this question. Over land, we already have this problem, right? The model predicts it's warming. The data, predicting was warming toward the present, but the data, it was warmer before, so it's cooling toward the present. Now, this marine proxy also shows the same thing. This difference is 0 minus 10K, 10,000 years ago. So you flip the sign, it's the same sign as this. So it seems to me that both over land and over ocean, you have, it's true, it's getting cooling towards the present, but our model shows it's warming. So that's the problem in my mind. How do we resolve this issue? And if you look at this construction, it's not just, it's a global, this cooling one trend, mostly it's caused by North Hemisphere, okay? Tropics, not too much, a little bit in the Southern Hemisphere, mostly caused by North Hemisphere. And that's also the place where you have most of the data. So that is the problem, okay? Now let's look at this more seriously. So I replot the observation here and replot the three model here. I showed you informally before. And so you can see that it is true. The data shows the cooling, the model, the three lines show the warming, okay? And the black line, I think, is the average of the three model. Now, just be sure, the model in this part, in the last 2,000 years, this model do produce little ice age, because once you have volcano effect, you produce little ice age. This simulation, we don't have little volcano, so it looks like you don't have that. But if you do have that, it'll produce little ice age like this. So it's consistent, little ice age, consistent in the deglaciation, but opposite in the Holocene. Okay, so that's the problem. About 1 degree warming, 1 degree problem. And you compare that with different latitude band, this global. And most of the difference is coming from North Hemisphere. You see, the data shows a very strong cooling, but the model shows ½ degree warming. Data shows 1 degree cooling, so it's 1/2 degree, okay? But also in the tropics in South Hemisphere, but mostly in the North Hemisphere. So that was a conundrum. The conundrum presented this way: how can global warming, how can global mean and the annual mean temperature decreases in the last 10,000 years throughout the Holocene against the global warming forcing, known global warming forcing? There's a CO2 rise about 20 ppm. And also we know the ice sheet is retreating, both trying to help you warming in our model, but in the observation shows this way. So how can it be possible? Okay, so that's in a sense, most people tend to put this as a conundrum between data versus model. To me, it was not data versus model. Model to me is just a way to help me thinking more quantitatively. I think it's a puzzle of data versus our understanding. Okay, we have the global warming forcing CO2 warming and ice sheet retreating warming. How can the global temperature become cooler? That's my conundrum. Okay, and also be careful in this context. We should most puzzling is global mean, annual mean, because otherwise radiation orbital forcing will play some role there. But we'll come back a little bit later on this. Now, I had a huge problem publishing my paper. The paper went to probably 5-10 journals, is all rejected because the major objection coming from the data people, they said, well, you got a model, say we worked for 50 years, thousands of people, we got data, show it's cooling, and you say we're wrong. No, it's impossible, okay? So that's the major objection, okay? But I think the thing to think about this, yes, observation is always true, as long as you didn't make a mistake in your sampling, whatever. But especially for paleo, we have to be careful because we don't have temperature observation beyond the instrument period. Everything of proxy is a proxy, okay? Therefore, its interpretation can be wrong, okay? It's not the observation is wrong, it's your interpretation could be wrong, okay? On the other hand, the model is true. A model is never a perfect model, never, okay? But a model, we know it contains quantitative physical laws consistent within the system. Therefore, it at least helps us understand that. And it's a quantification of different competing mechanisms, putting all this together in our Earth system model, which now we call the complex model. We got a Nobel Prize. So I think it's not obvious, has to be one is right, one is wrong. But as a modeler, we come back, say, well, what potentially could be wrong in our model, okay? And that goes back to the mechanism, okay? As I said, this observation of the global cooling. If you look at the forcing, first look at the orbital insulation forcing. As I said, this different latitude, this is time less 10,000 years. You can see that in winter, this winter, it's getting very cold before because because we are further away from the sun. So, but now it's getting closer to the sun in January. So it's winter is warming, summer is opposite, is cooling. And you mean actually is this effect? It's called obliquity. It's Earth's the tilt decreased a little bit. So this is indeed the annual mean, because if the Earth does not tilt, we'll have zero insulation in the pole, maximum insulation on the equator. But because the Earth tilts like this, so we polar region, we can get some insulation, but the total insulation is fixed. So basically we reduce some in the equatorial region. So you can see that the pole region, it is getting, because obliquity, it is getting cooler towards the present. But in the middle latitude and the tropics, it's getting warmer. Global mean is zero, because no matter how you tilt, the total insulation is same. So the global mean is zero. So the orbital forcing does not give you a simple reason why global mean, annual mean, you have warming, because average is zero if linear. Now, come back to the CO2. The CO2, it is true, CO2 increased about 100 ppm before from deglaciation. In the Holocene, it's a very weak change, but it does increase by about 20 ppm, okay? So it's not, that 20 ppm is about, it's about 10% of the 300 ppm. That's not negligible either, okay? So, but anyway, it's a warming effect. And then we know there's ice sheet retreating, so that's also warming. So these two forcing give you warming effect. The orbital, unclear, let's say linearly it's zero, this to give you warming. Other thing, there's solar activity. This is solar activity. There's no clear trend, okay? And then people say maybe there's a volcano. This is volcano activity recorded from Greenland, from Southern Hemisphere. You know, there's the volcano activity actually shows, if anything, it shows actually the opposite, and there's no clear trend. And we know the medieval warming time was because the volcano was less. The Little Ice Age was a time volcano was more volcano, but you can't. Well, now we are cooling toward medieval warming, so you cannot have negative volcano because medieval basically don't have much volcano. You can't have negative volcano make it even warmer before, right? So that volcano doesn't work. So it's not clear. That's the problem for understanding. Now in model, we can show this because the model, we did an experiment. The black line is experiment I just talked about before. It was warming by about 1 degree in the last 10,000 years. We did experiment for separate forcing. This is the experiment using pure CO2 forcing. So you can see that the CO2 forcing can increase about 0.3 degrees during the Holocene, okay? And then this is ice sheet, okay? Retreating ice sheet, green one, you can increase about 0.3 degrees. And then there is orbital one. The orbital one, it's not clear. It's not clear warming or cooling. Actually, I have a bar here. This shows is a PMIP experiment. It's about 40, 50 models around the world. They all did experiments 6,000 years ago. And if we look at the mean annual temperature compared with present day, you know, it's actually a little bit warming, but you do have a little bit spread, okay? So the model on average, there's no clear cooling trend either. So, and there's other two models showing similar thing. So the warming, greenhouse warming gave us 0.3 degree warming. Ice sheet about 0.3 degree warming. And the climate model sensitivity is okay. For example, I'm presenting the model. I was using the NCAR CCSM3. During the last deglaciation, because the CO2 increased by about 100 ppm, okay, 180 to 260, okay. So this is constructed, same proxy constructed, and they do show warming about 3 degrees. Our model basically produced very similar to this, okay. So it shows that my model sensitivity to CO2 is okay. It's not our model sensitivity is too big or too small, okay? So come back to the question. The warming is, we know there are two warming forcing. Greenhouse increase, 0.3 degree warming, ice sheet retreating, 0.3 degree warming. But are there mechanisms that will cause cooling? And there is a talk about the vegetation feedback. Basically, in the Holocene, in the early Holocene, because summer is very warm, you have more, let's say you have more trees. Let's say the boreal forest, you have more boreal forest, it's darker, it absorbs more sun. So that will help you produce warming at that time. But at least in our model, that effect is included. Our vegetation is changing with the climate, okay? So how big effect is this on global annual mean? And it's not clear, okay? It's probably too weak, okay? Or you have some missing feedback. That's another possibility, okay? And the other possibility in our model, we didn't put it was a dust. Because 10,000, 6,000 years ago, it was very wet in Africa because summer insolation strong, monsoon was strong. Therefore, you have more vegetation. Therefore, you have less dust. And therefore, it could be that we have less dust at the time. So then you have more sunshine. So that can be a warming mechanism for that period. We didn't have that, but I'll come back to that later. It's not very strong, okay? And then you can say the orbital forcing, maybe it's not linear. It's not homogeneous everywhere. It may be complicated, okay? But as we showed in the model, it's not very strong. So, but there's one thing we do need to notice, the global feature. Even with pure orbital warming, okay? The global mean, as I said, it's not warming much. It's about the same. But you look at different latitude, it is true. The polar region, it was warmer before, so they are cooling down towards present. Tropic is opposite. That's just basically simple mind. You can think about that orbital forcing. As I said, the obligatory forcing, annual mean forcing, is warming at the previous time. compared with present day. So it was cooling. So this is okay. This is not a major issue. And so we shouldn't be surprised if you have a core, an ice core showing cooling. You say, oh no, it has to be cooling, global mean cooling. No, ice core is in high latitude, and it should show annual mean cooling. No problem, okay? And now the early part, we talk about China, that part actually is not clear because it's close to 0 point. So global average, this is about 0, that's here. It's 0, there's no warming, okay? Because orbital forcing. So China, mid-latitude happened to be the node point. It's about the same as global. That's why why China has a big difference between model and observation. It's the same as global story. The dust, yes, later we did an experiment. You plug in the dust in the model. This is a kind of almost upper bound of the dust you can produce from Africa. Yes, you can produce a little bit cooling, about 0.3 degrees, okay? And mostly in the northern hemisphere, okay? You can see the temperature here. Of course, mostly over Africa. So you can contribute some, but still you cannot change the basic story, okay? You can't change the basic story. But now let's come back to the data. Is it possible some of the data have some problem? As I said, most of the data in the micro papers coming from sea surface temperature, marine temperature. And there's one huge problem in temperature reconstruction. It's that between two types of classical measures, they are inconsistent. This is the paper talking about that. It shows that in different regions around the world, you group the data into two methods. One is alkaline SST, one is magnesium SST. You can see that they are opposite trend. Not in one region, in almost all the regions. Magnesium SST is getting this is a early Holocene at this time, so it's cooling, but alkaline SST is warming. Okay, so all of the region, and actually that was the reason I started to think it's worth writing the paper. Not because I had a model before, because I realized that in observation, the data, there's also a huge uncertainty, okay? Because this is everybody, they both think they are annual mean temperature, but yet they got the opposite trend. So clearly there's a problem, okay? This observation versus observation has nothing to do with model, okay? So at least to me, it indicates there's uncertainty in observation. And I'll skip this just to say that the observation has uncertainty. So one possibility is that we do know that in summer, the insolation 10,000 years ago was warmer than today because we're closer to the sun in June, okay? So the summer temperature should be cooling, okay? That's not surprising. So, so I said, well, what about suppose the surface temperature proxy recording summer instead of annual mean temperature, okay? Now we can, in the model, we can test that. We say, this model annual mean temperature is warming, but if I use summer temperature in those proxy records location, what will it look like? Then you can see indeed you produce a cooling, not as much as them, but it is already a huge difference from annual mean, okay? So it indicates that one possibility of this conundrum is that maybe the proxy is referring to summer temperature instead of annual mean temperature, okay? Now that was about years back, 2014, when I read the paper, and it was a summary at that time. It said, global mean annual mean temperature decreased throughout the Holocene against global mean warming forcing of rising CO2 retreating ice. That was a conundrum. The hypothesis is that the seasonal temperature bias maybe potentially is affecting the proxy, therefore causing this bias. But that was a model hypothesis. Now, this is ultimately a data problem because you can never, it's argued, model is always like this. And even the most recent AR7, it has the same problem, okay? Of all the improvement in the model, it's the same problem, okay? So I almost forgot about this because I'm not data people, I can't do much. But my collaborator Yair from Rutgers and clever postdoc, Sam, they stick to this problem, find a very interesting, simple way we work together to use just observation to show that probably there's seasonal bias. If we remove seasonal bias, we'll get any mean temperature. It is warming, just like in the model, okay? And so that was last year. So the idea was this. We are interested in the Holocene, okay, this last 10,000 years. But Holocene is a little bit messy. First of all, the signal is small. Second, there's CO2. We talk about CO2 ice sheet. And so they said, well, what about if we go back to last interglacial, okay? See, this is the CO2. You can see that there's a 100,000 year cycle. That's great, interglacial cycle. Last interglacial is about 125,000 years ago. And CO2 is more or less flat. And ice sheet is minimum, like today. And but the important advantage is that this insolation seasonal cycle is about twice today. So the point is that the seasonal signal last 10,000 years ago, it was bigger, while other things are sort of flat. So the seasonal signal might be more pronounced. Therefore, just to know that this is also interesting period. This is civilization. This is a period where the human Homo sapiens moving out of Africa, spreading toward the world. Okay, because of this climate effect. There are recent paper talking about that. But anyway, so come back to our method. It's actually a very simple method. So basically, putting it this way, this is our this is their record near Papua New Guinea. They construct temperature, magnesium, calcium temperature like before. Okay, then you say, well, what months of insolation it looks like? Okay, because the insolation different months is different. Some are cooling, some are warming. Basically, statistically, you do a regression. Again, different months of insolation. You find that you say, okay, assuming it's linear response of sea surface temperature, then we regress it out. So this is they found that for this case, it's October insolation similar to this. Then they say, okay, we regress out this part. We're leaving the residual. The residual, we think, hopefully, is annual mean because the seasonal signal is gone and you have the residual. This, the dark blue, was the residual, okay? So you can see that in this residual, instead of a cooling, it's warming. This for last interglacial. Then, because this regression, you got a big seasonal signal from ST, you use the same regression coefficient to do that for the Holocene. Their data extend all the way to the Holocene. In the Holocene, this is the original data. Okay, the original data, the with the square, it shows some kind of weak cooling. But after they remove the seasonal signal, using last interglacial data as a calibration, they do produce warming. They produce this warming, the black, the square line, the square marker. Okay, now there are several major hypotheses in this method. It's a semi-empirical, semi-physical. So first thing, the minimum thing we can test, at least in the model, because we also run a model. I also run a model last 300,000 years. So you say, can I do the same thing using the same statistical method, using my model ST as a synthetic observation? That's the dashed line here, okay? The dashed line in this location, I do have cooling. And then if I regress this out, and then I get this warming. And apply to Holocene, it's the same, okay? So at least this method, it works in a complex Earth system model, okay? So the statistical method. So assuming that's complex enough, representing real world, and probably this also works in the real world. So the method is very simple. There's no point to go to details. All I'm saying is just linear regression, regress seasonal out, then you're left with a residual. You call this residual. You think this is the annual mean because seasonal response is out. Okay. So using this method, as I showed before, you can apply to not just one data, the original I showed you was one data near Papua New Guinea. Now you apply this to all the tropical, subtropical data. So you can see that for global, originally data, it was cooling. But after using this called ST method, remove the seasonal signal, I got a warming in the Holocene, okay? Just like in the model, okay? And we apply this to the model, that's the line without square. And you show this in the North Hemisphere subtropics, South Hemisphere, and this is in the, this is the 40 to 40 degree. This is, sorry, this is 40 to 40 degree. This North Hemisphere, this is the tropics, equatorial region, this is South Hemisphere. This is 40 to 40 degree, sort of like, most like global, okay? So that's basically what this, so this is a pure, in this method, remember, we only use a simple regression. You assume the seasonal response is linear, and that's two major assumptions, and then you derive it. We didn't use model. The model here used is only for test and see if this method works in the model. If it doesn't work in the model, then because then we wouldn't trust this in the observation either, because model already disproved that. So that's the story here. Shows that originally the observation shows the global temperature is cooling, okay? And in our ST, yes, we also show it was cooling, but in our ST, if we use our filtering method, we remove the seasonal cycle in the last interglacier, then in the Holocene, we do produce this warming. And it's very similar to observation, and sorry, to the model. And in the model, we can show that this warming actually mostly is caused by the 220 ppm CO2. Okay, 0.3 degree warming, that's about right, because we have a double CO2, we have about a 3 degree warming, and the 0.3, that double CO2 is 300 ppm. So now I have 20 ppm is about 10%. So we have 0.3 degree warming. That's about right. The magnitude is about right. Okay, so here's the conclusion. That is, the original conundrum was this: how can global mean annual mean temperature cools throughout the Holocene against the global warming forcing of rising CO2 and retreating ice sheet? The conclusion now, based on data alone, this is not based on model, okay, based on data alone, the sea surface temperature seasonal bias can indeed be large. So if it can be removed, okay, then the global mean temperature is indeed becoming warming in the Holocene, consistent with our understanding as well as our IPCC model. If that's the case, of course, now present day is the warmest, not just in the last 1,000 years, but it's warmer in the last 10,000 years and even longer, 100,000 years, because of the glacial period in the previous period. So you can say that, well, this is all marine data, right? This is marine data. What about land data? Lots of data, land data show this cooling. Well, I don't know because I'm not a data guy, but I do know that it is also possible at least some land data also have seasonal bias, okay? For example, the borehole temperature. This was actually recognized before, Michael Mann. He showed that, basically his paper showed that the borehole temperature, it's using the temperature profile along the drilling and representing past the temperature change, is more representative of summer temperature instead of annual temperature for a very simple physical reason. Because in winter, you have snow, so the borehole temperature in the ground is insulated from air temperature. In summer, you don't have snow. Yes, the borehole temperature is connected with air temperature. So that's why in borehole temperature, at least, it's more favored for summer temperature in this case, okay? Now for other proxy, I don't know. Even for the most recent, 1 or 2 years ago, the new proxy, this is all different kind of proxy, marine proxy and terrestrial proxy, all of them calibrated towards annual mean temperature, okay? And this is all the data shown here. You can see that, like, for example, the terrestrial, they're still cooling, okay? Just like I showed before, column, they still show cooling, okay? And The marine proxy, let's say we already did. If we use our method, we can separate them apart. For this proxy, why is that? I don't know. Okay, so I'm puzzled why all the independent proxies still show the cooling. Now I have to say that the seasonal bias is not the complete solution because it does not work in the south hemisphere. Look at the south hemisphere. The observation shows cooling, our model shows warming. You cannot use the seasonal bias because in the south hemisphere, as I said, the seasonal change 10,000 years ago is opposite to today. So if you use the summer season in south hemisphere, you get even stronger warming, okay, instead of cooling. So it only works tropics and the north hemisphere very clearly. South hemisphere is not clear. It's not clear. Okay. So I think their effort now trying to identify south hemisphere ST, but south hemisphere also we have less observation. So I'm trying to further identify this issue. And there are also potentially other mechanisms, which I'm not going to talk about in the model. Maybe we're missing something, especially in the south hemisphere. Okay. So a critical summary is that the Holocene temperature, how it's evolving, even though almost all the proxies, they think going this way, but we think the true annual mean temperature actually is warming because atmosphere CO2 is warming and the retreating ice sheet, okay? And this mostly is caused by seasonal bias, okay? Now, ideally, we are using a method, we call it residual method. Ideally, if people truly understand the annual mean temperature proxy, that would be ideal, okay? But so far, we don't have that capability yet. That's something really require further study from the data community. And so the issue still remains. I don't understand why all the proxies in the land consistently tend to show cooling opposite to the model. And the model may be missing some feedback. And south hemisphere is the issue, okay? Because seasonal bias doesn't apply to south hemisphere. So if there's difference, there got to be something else, okay? Maybe model bias has some missing mechanism in the model. Finally, just putting this in a broader context, we are talking about the Holocene here, warming or cooling. CO2 is increasing a little bit, and the warming or cooling. There is an interesting question. Why CO2 started to increase 20 ppm 6,000 years ago? It's here. This is 10,000 years ago. You look at the CO2. It started to increase about 8,000 years ago, okay? And but in the previous 4 glacial cycle, CO2, once you reach a peak, you start to decrease. So if you use that analogy, CO2 should have decreased by 20 ppm by now instead of increasing. So there's a 40 ppm CO2 difference between this cycle and all the previous cycle. This was noticed by Bill Rodman. It's called Bill Rodman. He hypothesized that this increase is caused by human activity, deforestation. So he hypothesized that human activity on climate already appeared 8,000 years ago. That's where our civilization, as I said, civilization started about this time, right? Now, that's still under study, right? So we are talking about if, in my study, I said, if CO2 increased 20 ppm, it will result in global warming. Yes, maybe data, if you remove seasonal bias, you also show that. Now, you go back one more step, you say, well, how can a 40 ppm CO2 rise stop the last glaciation? Because we should enter into glacial period if we follow the pattern of the last few glacial cycle. Instead, we are actually not. Is it caused by the 40 ppm increase of CO2? That question will require a model of ocean atmosphere as well as coupled with ice sheet. Can we produce that? It's not a trivial issue because in the coupled model, we haven't been able to perfectly produce this glacier interglacial period yet, because the ice sheet dynamics also become complicated. You go a step further, even more complicated from Earth system. How can a 40 ppm CO2 be generated by climate carbon system, right? If follow previous cycle, we should have CO2 just decrease. How can this be increased? Is it really caused by human activity, or is it caused by some anomaly in the last cycle? Okay, this problem is not solved at all. Okay, so it still remain open. So there's still lots of questions remaining to be studied during this period, from not just from temperature, but all the way to ice sheet, to the CO2, and to human activity. Okay, thank you very much. That's my talk. Yeah.
Thank you very much, Professor Liu. Thank you for this very exciting talk. Yes, and seems like you have solved a long-standing puzzle, and congratulations on that. Now, I would like, we have time for several questions. Now, I would like to invite the audience to ask questions.
Thank you. Yes. Yeah.
Yes, please.
Still
yeah,
muted.
I cannot hear you. Yeah, can you?
Okay, still muted.
Okay.
Yeah.
Hey,
Okay.
hi,
Yeah.
Professor Liu.
Yeah, nice to you here.
I'm Zhou Hui. So
Yeah.
thank you for this very, very interesting talk. And so I just want to ask your opinion about the recent publication in Science Advance. So Jessica Tierney is one of the course. I can't remember the first order, but they put, I think they put hypothetically more vegetation feedback in the climate system, in the climate system, and then they produce relatively warmer early Holocene or the mid Holocene. So what do you think about this idea? Is that a good solution for the conundrum?
Well, I don't know this paper, more recent paper. I heard about people talking about that. I think the vegetation feedback is a hard problem because it's hard to quantify. Now, in a model, I can always tune my parameter. Okay, you know, I can get my vegetation feedback bigger. Okay, and but given the vegetation feedback parameter people already have, think optimal, they already calibrated with observation, and at least in our model, we have vegetation feedback is really small. In our most previous study, the vegetation feedback, the warming effect is small, and especially for global. Now locally, you know, boreal forest maybe, global, it's small. So I think the vegetation feedback is a quantitative issue. Qualitatively, I believe it's true. It's a warming effect. The question is quantitatively, how big can it be to global temperature? Okay, remember we have 1 degree difference, and the model shows half degree cooling, data shows half degree warming. So there's a 1 degree disparity. How much of the vegetation feedback can contribute to the difference? And at least in 1 or 2 models, we already have vegetation feedback in that. So it's, in some sense, it's already included. So now how do you know? Suppose you use a vegetation model, you change another different vegetation model. Suppose you do produce this warming at that time bigger. How can you, how do you know your vegetation model is more correct than other vegetation models for feedback, right? So to me, it's this question, okay? The vegetation feedback is very hard to separate apart from observation to compare. Yeah, so it's interesting idea, but I think remains challenging to calibrate the vegetation feedback. How do you know your vegetation feedback is, the magnitude is right? That's hard part, I think.
Thanks.
Yeah.
Okay. Any other questions? Yeah, if you have questions, yeah, you can just unmute yourself and speak up. So, Professor Liu, I have a question because I don't have much background in this field. So, just from point of view of modeling, So when people propose a different modeling method, are there any free-fitting parameters, or all the parameters are based on certain
yeah. The climate model, the models we are using are the models for the IPCC current climate model. And you know that recently the Suki Manabe got a Nobel Prize for this climate model. And this class of model basically is fluid dynamics, Newton's second law, then plus thermodynamic, first thermodynamic law. Is based on rigorous physics law. But they are always parameters because the model, we have finite grid point. We cannot resolve every cloud. Even if you resolve cloud in the future, you cannot resolve every droplet. It's impossible, okay? Yeah. So you have to have some parameterization. That's why we call it parameterization, okay? And now people studying models, that's a career. They building models, they testing with satellite observation, all the observations. They think their parameter is probably right. That's why they have this state-of-art model. And but still, there's a big uncertainty. For example, we know that the cloud is still a big problem. If you look at the model, the cloud feedback is very different. Actually, most of the, you see the IPCC, why is the spread between 2 to 7 degrees, 4 degrees? Most of that comes from cloud. The cloud parameterization is very different in different models it produces. The fluid dynamic part is a solid, it's almost the same. The Newton's second law, there's nothing to play with, it's fixed. But the cloud part, how do you look across? I have a box, 100 kilometer box. How many clouds? How do I parameterize each cloud there? It's a very difficult issue. And another thing is more recently is this the aerosol feedback, because the aerosol has complicated thing. Aerosol itself directly reflects sunlight. Maybe it's cooling, but aerosol also affects clouds, because clouds, you need the aerosol as nucleus to form clouds. If you have no aerosol, it's very, very hard to form clouds, okay? So that's called indirect air. So it's getting, these two things, I think, the biggest uncertainty in climate model. So that's why nobody trusts a single one. They say we kind of assume everybody has randomly, maybe a little bit bias. So we use the ensemble. We look at that. Look at that. But the way I think to think about it, as far as global warming is concerned, that because all of the models show that global warming in the future, right? And there could be one could argue, say, well, since you cannot simulate everything, you cannot prove everything right, the model may be wrong. So I'll put it this way. You created your model with all the physics laws we know, okay? Then use your model to compare with whatever past observation we have within the same consistency, then you predict the future. If you can predict global cooling, then I'll be very interested to see that. No model has done that, okay? So I think in that sense, we have definitely some confidence on our model, but certainly there is there also uncertainty within model. But that's not the reason to say the anthropogenic warming, the warming caused by anthropogenic forcing effect is wrong in the model, because we think the model is well beyond that criteria of that. And that's why also the past climate, why it's important, because most models are built on instrument data last century. So in a sense, the parameter was tuned toward simulating the last century pretty well, okay? Therefore, the past will be an independent test because they didn't tune their model to simulate the past. If you can simulate past very well, then you say, I can simulate the past, that's independent. There's no tuning. Then I trust my model for the future, okay? Now for my Holocene problem, there's an issue. The past, there's an issue. How accurate is the data? Okay, so that's the issue, okay? The data, as I said, observation, the data is always correct. You take, you get a sand. The sand is truth, that is correct. But how do you interpret it? That is the uncertainty. I think that's the issue. I think, overall, I think, certainly data drive a lot of science, but I think this interplay between model and data help us to improve our understanding. Actually, this is Yair, my collaborator, because we are very familiar, we were buddies when we are students together. So when I first started with him, he has magnesium calcium. I had model, that was 15 years ago. We are opposite. He said, no, I'm not working with you anymore. Your model must be wrong. My data must be right, okay? And, but later we wrote that paper, 2014. He changed in his mind, 180 degrees. This last paper he was main driver, the last one with his postdoc. I'm a model, I'm sitting on the bed. They are the data guys, they are thinking. So then they pushed all the way and get that result. So I think it's really through this model data interplay, I think, help improve our understanding. Yeah, certainly model has bias. We know there's some bias we're thinking to do in the future to test, but yeah.
Thank you. Any other questions from the audience?
Professor, can I ask another question?
Sure. Yeah. You are expert on data. I know that. Yeah.
So, Professor Liu, so I'm working on the proxies. I know that it's really difficult to resolve the proxy seasonality the problem, and also know that perhaps for myself, I'm working on the organic proxy, so that mostly that would be biased towards summertime. So as you said, but so it seems to me indeed it's very difficult to from data perspective to get the the pure winter temperature record.
Yeah.
But my feeling that actually there is some indirect evidence that for example the winter monsoon, East Asia winter monsoon. But I know that still that topic is also controversial. But it seemed to me that indeed that in recent years there are a couple studies suggest that the Holocene winter monsoon actually is strengthening. So toward the present, it's getting stronger. So
that's interesting. Interesting to know.
So I mean, there are many many problems, many controversies. So so I mean, if that if we think that the recent reconstruction of the winter monsoon say is correct, so that will impact your the winter temperature simulation in your model, because again no pure winter temperature from proxies.
Yeah. Well, the winter monsoon, I think it's in the model. I think it's weakened towards just because solar insolation. It's a very simple reason. There's nothing fancy. I had a paper with Wenxing, on this summer monsoon, winter monsoon. The South China Sea proxy seem to indicate, but that's mostly on deglaciation, I think. Yeah, so last deglaciation. But anyway, my impression when I look at the model is that the winter, summer, they tend to be in phase, intensity tend to be in phase, just because the seasonal cycle of the precession forcing, at least in the first order. So, so I mean, that's why in SAM, this paper, they don't know what's the direct way to resolve it. So they use a kind of a inverse method, right? Sort of regress out of the most likely seasonal signal. It's a kind of a method out of desperate, because they don't know what to do. And so they did this way. I think it's very clever, it's one approach. And certainly, if you think the response is a linear response, that method works. Because if it's a linear response, that's a linear regression, you should be able to fill that, okay? And of course, one can argue complexity, but that's why we're testing the model. In testing model, all the complexity people talk about. After we published paper, we got 6 or 5 questions. Okay, we keep replying, and 3 of them are published, and 2 or 3 are published. Others they just reject it at the front, and the editor decide not to publish. So it mostly is on our method. It's true. We admit our method is not. It's a statistics method. You have assumption, linear, assumptions, and but we tested, at least we tested in the model. We know with our best knowledge, we just answered Professor Zhang. This is to our best knowledge, this IPCC model with CI feedback, vegetation feedback, all of them are, to the known context is in our model. We tested the method works. Okay, so that gave us some confidence on the method. Yeah. So yeah, I think it's really in the future still maybe one day. Well, that's why most people think this, because it's hard. Just like you say, it's hard. Yeah. So everybody just forget about, just do this. But isn't it true? You think about my question, forget about model. How can it be possible? The ice sheet retreating, CO2 increasing. How can it be possible the global temperature increases? Vegetation, dust, other things, it becomes a quantitative issue. Okay, so how can that compete with this warming? And it may be actually very important. Suppose, let's say the other feedback is not well taken into account. Let's suppose the data is true, still cooling. Then there may be something feedback, dust feedback, vegetation feedback may be very wrong in the model. That's another possibility. Yeah. So, but now I do think the model still have bias as the missing things. But I think the first order, the model is right. Probably there is a tuning there. Okay. So yeah, the vegetation. I don't know that paper. Maybe you can send me that paper, the most recent one. I've heard about it, but I haven't seen the paper about vegetation one.
Okay, I'll send you.
Yeah, it'll be curious. I'm curious because I worked on vegetation feedback a while ago. I know all of this, and so I know it's very tricky, the vegetation feedback, and the parameters are very tricky too. Yeah.
Mm-hmm. Thank you.
Yeah, thank you very much, Professor Liu. Thank you for thank you again for this exciting talk and for the inspiring discussion. Yeah, and hope in the near future we will have the pleasure to invite you again to come on campus in person, to visit us.
Sure. Love to. Okay. Yeah.
Okay. Thank you very much. And then now this session is concluded. Thank you. Take care.
Thank you very much. Thank you. Yeah.